Now in this video, we're going to take up the next chapter on torsion. So here, what is the pure torsion? A member is said to be in a state of pure torsion if it is subjected to a torsional moment not accompanied by any other forces such as bending or axial force. So that means you have only a torsional moment without having any bending or axial force is called a pure torsion. So what is the angle of twist? Angle of twist is the deformation of a circular shaft when subjected to a pure torsion. So that means when a shaft is subjected to one end is fixed and the other end is subjected to a twisting moment or the torsion moment, the angle of twist will going to take place, which is theta, which is the deformation of the circular shaft. So then it is subject which will going to be a pure angle of twist. So when you're considering that, take any line capital OA, so that is between these two, on the outer surface of the shaft. The line OA is parallel to the longitudinal axis of the shaft, that is OO1. So now if a twisting moment or torque, that is T, is applied as shown in the figure at the free end, then point A moves to A1. So angle AOA1 will be the angle of twist, which is measured in radians over, this is the angle of twist which measured over a length L. The boundary condition for theta. So what is the boundary condition for theta? That is when x is equal to 0, so that is at the center. So what will be the angle? Theta x will be equal to 0. When the value of x is equal to L, theta x will be equal to theta. So that is the angle made by this. So therefore, for pure torsion, angle of twist theta is linear. So that is on the longitudinal direction. Therefore, at any section of theta will be equal to theta by L into x or theta into x by L. So next we are going to take the assumptions. What are the assumptions which we make in the theory of pure torsion? So point number 1, the material of the shaft is homogeneous and isotropic. That is, the material of the shaft is uniform throughout. The normal cross section of the shaft, which are plane before twist, remain plane even after twist. That is, no warping will going to take place. So the shear stress is directly proportional to the shear strain, hence the material that of the shaft which obeys the Hooke's law, that is, stresses are within the elastic limit. The twisting along the shaft is uniform. And point number 5, the circular sections remain circular. Thus, all radii which are straight before twist remain straight after twist. Therefore, the point number 6, the torsion is uniform along the length. So next we will going to consider the derivation of the torsional equation. What is the shear stress produced in a circular shaft subjected to a pure torsion? So when you are considering a shaft of length L of diameter D, that is capital R, fixed at one end and free at the other end, take any line capital PQ on the outer surface, that is on this surface, on the circumference, outer surface of the shaft. The line PQ is parallel to the longitudinal axis of the shaft, which is perpendicular to this O, that is O on this side. If you take it in the top view, you will be able to understand that you will going to be the center line of the longitudinal axis of the shaft. So one should have, if the torque is the T applied to the shaft at the free end, then the point Q moves towards Q dash. It is assumed that this line remains straight and moves in the same plane in which it lies. So the angle between PQ and PQ dash is angle QPQ dash, which will be phi, which is the shear strain. Angle QOQ dash, that is the angle of twist, which will going to be theta in length L. Let small l will be the length of the shaft, and capital R is the radius of shaft, and theta is the angle of twist, and phi is the shear strain. So N or G or C will be equal to the modulus of rigidity. MT or capital T is the torque applied at the end capital Q. So tau is the shear stress induced on the outer surface of the shaft. So when you're considering that, what is the shear strain of the outer surface of the shaft? Shear strain, which is phi, will be equal to distortion per unit length. What is distortion per unit length? Distortion at outer surface divided by the length of the shaft. What is the distortion of the outer surface? The distortion of the outer surface is Q to Q dash, that is on this side, which is the distortion, which is nothing but Q dash Q by L, small l. That is QQ dash, what is the length? It can be QQ dash by PQ, which is equal to the length of the opposite side by the adjacent side, therefore, which will be equal to tan phi, which is opposite side by the adjacent side, which will be phi. What is the shear stress of the outer surface? The shear stress of the outer surface, small q, will be equal to QQ dash by L, which will be also from the end view. What is arc of QQ dash? Arc of QQ dash will be equal to capital R into theta. That is OQ into theta. That is equal to R into theta. Substitute the RQQ dash will be equal to, therefore, QQ dash will be equal to L into phi is equal to R into theta. Therefore, phi will be equal to capital R into theta by L. We call this equation as 1. So for a given torque capital T and the length of the shaft is constant, and therefore shear strain is directly proportional to its radial distance from the center of the shaft of the section. Hence shear strain is 0 at the center and the maximum at the outer surface. Therefore, shear strain at any radius r, which is phi 1, will be equal to r into theta by L, small r into theta by L, because at any other radius, which will be small r. If it is at the outer surface, then it is capital R into theta by L. So call this equation as 2. So from Hooke's law, what is that? Modulus of rigidity will be equal to shear stress by shear strain, which is G will be equal to shear stress is tau by shear strain is phi. So tau by what is shear strain? Phi R into capital R into theta by L. So therefore, so you will going to get it as tau by R. Tau by R will be equal to G into theta by L. So what you can do is you can cross multiply this. G into capital R into theta by L will be equal to tau. So take that capital R down. So therefore, and cross multiply, tau by R will be equal to G into capital G into theta by L, which is called this equation as number 3, where theta is in radians. So for a shaft subjected to a given torque T, the value of G and theta and L are constants. Hence, shear stress is directly proportional to the radius R, capital R, which is the radial distance from the center of the section. Hence, shear stress is 0 at the center and maximum at the outer surface. If small q is the shear stress at the radius small r from the center of the shaft, then tau by capital R will be equal to G into theta by L, which will be equal to small q by R, which is called this equation as 4. So from this, we can be able to derive the torsional equation. Now we can have the relation between the torque and the shear stress in a solid circular shaft. So what is that relation between torque and the shear stress in a solid circular shaft? If you are considering a solid circular shaft of capital R and considering any section, which is a radial section of inner radius of R and the thickness as dr. So consider a solid circular shaft subjected to torque capital T. The maximum torque transmitted by the solid shaft is obtained from the maximum shear stress. Now consider an elementary ring, circular ring of thickness dr and at radius r from the center of the shaft. Let capital R be the radius of the shaft, mt or capital T is the torque, applied torque, and small q is the shear stress at the inner induced in a radius of small r from the center. and tau max or tau is the maximum shear stress induced at the outer surface. So from this, what is the area of the circular ring? The area of the circular ring, capital dA, will be equal to 2 pi r into dr. So that means if you are considering this as the cross section, if you cut it and open, it becomes a rectangle of thickness dr, and then the thickness and the perimeter will going to be the circumference of the ring, which will be 2 pi r into thickness is dr. So therefore, you are going to get it as 2 pi r into dr. So equation 4 implies that is tau by r will be equal to small q by r, where the small shear stress at the radius small r will be q will be equal to tau into small r by capital R. Shear force at the elementary circular ring. What is the shear force? It is shear stress into area, dF, that is shear stress in the ring into area of the ring. So therefore, dF will be equal to tau into R by tau into small r by capital R into what is dA, that is area of the ring. It is 2 pi r into dr. So on simplification, you will going to get tau by capital R into 2 pi r square into dr. So torque on the elementary circular ring, which will be dt, will be equal to df into distortion of the ring from the center, which is df. You substitute the value of df as tau by capital R into 2 pi r square into dr into r, which is the distortion of the ring from the center. So on simplification, you will going to get it as tau by r into 2 pi r cube into dr. So total torque or torsional resisting torsional moment, T capital T will be equal to integral of 0 to r into dt, which will be equal to integral of 0 to r, and substitute the value of dt as tau by capital R into 2 pi r cube into dr. So taking tau by r into 2 pi as the common factor or the constant which is outside the integral sign, which is the integral of 0 to r into small r cube into dr, which will be equal to tau by r into 2 pi 2 pi into r to the power of 4 by 4, applying the limits of 0 to capital R, which will be equal to tau by r into 2 pi into capital R to the power of 4 by 4, which will be equal to pi r to the power of 4 by 2, because 2 gets cancels, and pi r to the power of 4 by 2 into tau by capital R. So substitute the r will be equal to d by 2, which will be equal to pi d to the power of 4 by 32 into tau by r. So where capital R will be equal to d by 2, so which will be equal to, that is torque is Jp into tau by r, where Jp is the polar moment of inertia of the solid shaft, which is pi d to the power of 4 by 32. Therefore, capital T by Jp will be equal to tau by r, which will be equal to, call this equation as 4. So you substitute the value of pi d to the power of 4 by 32 as Jp, which will be into tau by r. So from equation 3 and 5, you will going to get it as tau by r is equal to g into theta by L, and T by Jp will be equal to tau by r. Therefore, so since from these equations tau by r and tau by r is on the same, is equal, therefore tau by r is equal to g into theta by L, which will be equal to T by Jp. So this will going to be the call number equation 6. So therefore, the maximum shear stress which will going to be there is only will be shear stress at the outer surface of the shaft. So from equation 5, we have T by Jp is equal to tau by r. So maximum shear stress tau maximum will be equal to T into R by Jp, which will be equal to capital T into R is small d by 2 by pi d to the power of 4 by 32, which will be tau maximum will be equal to 16 into T by pi d cube. Call this equation as 7. Therefore, the shear stress is 0 at the center of the shaft and varies linearly along the radius, reaching the maximum value at the outer surface. Therefore, the equation 6 is known as the torsional equation, which is T by Jp is equal to tau by r is equal to g into theta by L, where if Newton and mm are used as the units for forces and distances, and mt or t will be equal to torsional moment in Newton mm, and tau or tau max will be equal to maximum shear stress at the outer surface in Newton per mm square, and capital R is the radius of the shaft in mm, and small l will be equal to length of the shaft in mm. G or small capital C is the modulus of rigidity in Newton per mm square. Jp or J will be equal to polar moment of inertia in mm to the power of 4. And angle of twist theta will be equal to angle of twist in radians. So this is how you will be able to derive the torsional equation from the equation. Thank you.